Hi friends, welcome to my YouTube channel. This is second part of lecture 14. In this lecture, we will calculate the various parameters for one phase half wave uncontrolled rectifier with R load. So this was the waveform we get in my previous lecture. So for this waveform, we will calculate the values of various parameters. First is average output voltage. So here we get this average output voltage, and I told you that average output voltage means net area under the waveform. Here positive area is equals to negative area. That's why we get average output voltage that is equals to 0. Now average value of output current. We know that equation of output current is equals to Vm by omega L 1 minus cos omega t. So simply integrating this equation of current from 0 to 2 pi and divide it by time period 2 pi, we will get the average output current. Now I tell you a very simple method. If you don't want to do this integration, then how can you calculate the average value of output current? So to do this, what we have to do, we have to bifurcate this equation of current in two parts. We can write this equation of current as Vm by omega L minus Vm by omega L cos omega t. So here this current has two components. This is DC component and this is fundamental component. Okay, now we know that average value of this cos omega t is 0. Okay, and average value of this DC component Vm by omega L is equals to Vm by omega L. That's why average value of this whole current equation will be equals to Vm by omega L. So this is simple way to find the average value of output current. And we know that maximum value of output current is 2 Vm by omega L. That's why we can write it as average value of output current is equals to 1 by 2 I naught max. Okay, and I naught max that is equals to 2 Vm by omega L, which occurs at pi. Now what is RMS value of output voltage? Here also there is no need to integrate. We know that output voltage that is equals to supply voltage and it is pure sinusoidal waveform, and average value of this waveform is simply Vm by root 2. Okay, so this is also very simple. Now we have to calculate the RMS value of fundamental component. This 0 1 means RMS value of fundamental component. So I told you that this current equation can be bifurcated into this DC component and this fundamental component. This Vm by omega L cos omega t is fundamental component. So here we have to calculate the RMS value of fundamental component of currents. That's why we will integrate only this Vm by omega L cos omega t, and we know that RMS value is 1 upon 2 pi integration 0 to 2 pi Vm by omega L cos omega t. Okay, and take square root of whole. On integration we get I naught max by root 2. Okay, so here also there is no need to integrate this because this is a cosine function, and we know that for cosine function the RMS value is simply equals to maximum value by root 2, and here maximum value is Vm by omega L. That's why we can simply write Vm by omega L by root 2. Okay, so this is very simple. If you know the basic concepts, then you can avoid the unnecessary integration. Okay, next is this load is current step. Why it is current step? Because here we can clearly see that this voltage and current waveforms are not similar. Here we get current only in positive direction, while here we get voltage in both positive and negative direction. That's why this load is current step. Again, this is half wave uncontrolled rectifier. Next is average output, total output power P naught. See, here you must note an important concept. That is, whenever the load is current stiff, okay, then in that case, output power P naught will always be written as V naught average into I naught average. Okay, while in case of voltage stiff load, that is resistive load, the output power is written as I naught RMS square into R. But here, because load is current stiff, and in case of current stiff load, we always write output power as V naught average into I naught average. Okay. Now what is conduction angle? Okay, so conduction angle means angle up to which diode conducts, and we know that during circuit operation of rectifier that this diode will remain forward bias, okay, from 0 to 2 pi. That's why we get conduction angle of diode that is equals to 2 pi. Here we see that drop across this diode is 0 from 0 to 2 pi. That's why conduction angle is 2 pi. Now what is excitation angle? Excitation angle is the angle up to which we get current, and we know that we get current up to 2 pi. That's why excitation angle is 2 pi. What is peak inverse voltage? So there is no drop across this diode. That's why peak inverse voltage is equals to 0. What is circuit turn off time? It is the time for which diode is reverse biased, and here we see that for no time diode is reverse biased. That's why circuit turn off time is equals to 0. So this is all about this rectifier circuit with inductive load. I hope you understand the concept, and thank you. Jai Shri Ram. If you got the knowledge and concepts from this video, then please like the video and subscribe the channel. You can give your views and ask any questions related to this topic in comment box. Also share this video with your friends because sharing is caring. Don't forget to press the bell icon to get the notification of my upcoming videos. Thank you.